So welcome to lesson 3.3, which is about scale-free phenomena. Now, scale-free behaviour is a very common property of socio-historical processes, and that's why we've got a whole lesson devoted to the topic. And in this lesson, we'll be encountering some of the more difficult mathematics that I'll be dealing with in this course, but we'll also be covering some important points that can be understood qualitatively. Okay, I've drawn up 4 graphs here. On the top we've got plots of y equals x squared, so this is a power law, y equals x to the power of 2. And on the bottom we've got y equals e to the x, an exponential law. And in each case I've drawn a graph that's on a smaller scale, so from 0 to 3, just from 0 to 3. And on the right hand side a graph that's on a larger scale, so this is from 0 to 30. And what we notice here is that with the power law, with y equals x squared, the two graphs look exactly the same. It doesn't depend upon the scale. The appearance of the graph remains the same on a small scale or a large scale. So if we took away the scale and looked at these, we wouldn't be able to tell what scale we were looking at. So this has the property of being scale free, or it exhibits scale invariance. But with the exponential graph, that's not the case. These do not look identical. In fact, they look very different. And if we took away the scale, we could tell that this one is on a larger scale than that one. So the exponential is not scale free, but the power law is scale free. So when we see scale free phenomena, it means that there is a power law somewhere involved, because it is power laws that are scale invariant, scale free. And the point is then that we find these power laws and scale-free behaviour in a wide range of socio-historical processes. So, for example, the severity of wars. By severity, how big the war is, particularly how many people are killed in the war. Power laws are seen in the sizes of cities. Well, I mean by the sizes, I mean the population sizes of the cities. It's seen in people's incomes. You know, people have smaller incomes and larger incomes, and there's a power law involved. It's seen in the citations of academic papers, academic citations. So some academic papers get cited a lot, and many get cited very little. So, and these are just some examples. There are many more. And I mentioned at the beginning of this course the Nobel Prize-winning physicist Murray Gell-Mann, who became interested in theoretical history towards the end of his life. And he talked about power laws, and he described power laws as a kind of middle-level theory, so that if you find a power law, you've got a kind of theory about your system. It's better than just seeing it as purely random. If you understand that it's a power law, you can start to make predictions about how it will behave in future, because you know it is scale free, for example. So it is definitely a useful thing to know about your system, but it doesn't really explain why we have a power law. And that's what what we really need, a theory that explains what generates this power law behaviour, or this scale-free behaviour. So finding a power law is only part way towards really understanding the system. And the trouble is that many people have sort of found power laws in systems like these kinds of things. They've found power laws, but they haven't really explained why that power law occurs. And so they're kind of sort of rested on their laurels. Oh, we found a power law. Yes, it's good to find a power law, but what we really want to know is what generates that power law. And so power laws have perhaps got a little bit of a bad reputation. And some people might even say power laws are rather trivial because it's very easy to find power laws, much harder to understand what's really going on that generates a power law. I think it's misguided to regard them as trivial. You know, they are really important and they tell us about the fundamental processes that are going on in socio-historical systems, and we will see some of the kinds of mechanisms that we might bring in to explain them. So yes, power laws, they're kind of ubiquitous, but they're not trivial. They're a really important insight into what might be happening, a really important clue to helping develop fundamental theories about socio-historical processes. Okay, so I've written up here the general formula for a power law. Y is equal to a constant, times x to the power of m, the exponent of the power law. And if we take the logarithm of both sides here, so we've got log y equals, well, taking logarithms converts multiplication to addition, so we'll have log of a plus, and then this will be m times log of x. So we need to remember that log of something like x to the m equals m log x. If we remember the lesson on exponents, you know, it's fairly straightforward as to why that is the case. But anyway, it's just something we need to remember. So we've now got log y equals log a plus m log x, and we could call that log a c because it's just another constant. So we'll just rename that as the constant c, and therefore we can write this as log y equals m log x plus c. And we can compare that with our classic equation for a straight line, y equals mx plus c. So what that tells us is that log y and log x are related by a straight line relationship. So if we plot log y against log x, we will get a straight line. So if we have a power law and we just plot y against x, it will look something like that. But if we plot log of y against log of x, we'll get a straight line. So on a double logarithmic plot with both axes logarithmic, a power law will appear as a straight line. So a log-log plot, double logarithmic plot, is a very useful tool for studying power laws. If we plot our data and we get a straight line, then it tells us we've got a power law. And we can also see that the slope of the straight line on the double logarithmic plot is this m, which is the exponent of the power law. And we've seen a special case of this with hyperbolic growth that we said for studying hyperbolas, which is something like y equals 1 over x. A double logarithmic plot is a way of showing it's a hyperbola because it will be a straight line of slope minus 1, and that's just a special case of this. Y equals x to the minus 1 is 1 over x, so the slope is minus 1. So it being minus 1 for a hyperbola, it will slope downwards. Slope of minus 1 slopes downwards. It's a negative slope, sloping downwards. Okay, so I said that we find power laws in socio-historical processes, and what we usually mean by that is that there is a power law distribution in the socio-historical data. So what we're talking about is a set of items that have a size associated with them. So it might be wars. S is the size, so that would be the severity of the war, the number of people killed. Or S, that might be the population sizes of cities, or it might be the sizes of people's incomes, or it might be the number of citations received by academic papers. All these things are things of different sizes. And so we have a set of items where the size can vary, the populations of the cities can vary, the number of people killed in the wars can vary. So what we're interested in is the number of items, n, of each different size. How many cities are there with a population of 1 million compared to how many cities there are with a population of 10 million? So we're interested in the number of each size. And when we say it's a power law, it means that that number is proportional to the size S to some power, alpha, the exponent of the power law. Only usually we're going to say it is minus alpha, because usually the larger the size, the fewer there are. So as the size increases, the number of that size decreases. So as the size increases, they get rarer. So larger wars are less common, larger cities are less common. So that is the reason for the minus sign there. So if we plot it on ordinary axes then against the size, the number of that size, so this is again the number of people killed in the wars, the population sizes of the cities. If it were a positive exponent plus alpha, it would go up like that as a power law. But with the minus alpha, we're taking the reciprocal of this. So as this gets larger, the reciprocal is getting smaller. As 3 is larger than 2, but a third is less than a half. So as the size gets larger, the number gets smaller. So that's with a negative exponent. And then on a log-log plot, which we've just said is I'll just put there log of n, which is a good way to study power laws. If it's a positive exponent, we'll see a line going up with a positive slope. And for the more usual power law distribution that we'll see, we should expect a downward sloping line, a line with negative slope, minus alpha. And now let's have a look at a particular example. Okay, so this is a table showing the sizes of wars. So it was Lewis, Fry, Richardson who collected data on the sizes of wars. His book is Statistics of Deadly Quarrels, as he called them. So this data is taken from his book. He was active in the early to mid 20th century. So the size of the war is measured in terms of the number of fatalities. So that is S in this case. And they're just classed into categories by order of magnitude. So wars that had fatalities in the thousands, there were 188 of those. So N of S is 188. Wars in the category of tens of thousands of fatalities, there were 63. Hundreds of thousands of fatalities, there were 24 wars. 1,000,005 and 10,000,002. And we can now plot these on a double logarithmic plot. And that's the size there. So here is a logarithmic plot. That's the number of a particular size up the y-axis and the size of the wars along the x-axis. So from 1,000 to 10 million, and the numbers from 1 up to 1,000. Well, 188 was the largest number. So wars in the thousands, there were 188, and 10,000s, 63, and so on. So we get a downward sloping line. So we have a power law. So the n of s is related to s by a power law, and the exponent of the power law is the slope of this line. And we can also consider, instead of the number of s, we can consider the frequency of a particular size. So the frequency of a particular size is the fraction of wars, in this case, that were of that size. So it's the number of that size divided by the total number. So that's the fraction of wars that were of that particular size. And I've plotted that here, so the fraction of wars of size s. So there are in total here 282 wars you can find by adding those up. So n of s over n is 188 over 282. It comes to 0.67, about 2/3. So 2/3 of the wars were in the thousands of fatalities range, and then 0.22 fraction of the wars were in the 10,000s range, and so on. And if the number is related to the size by a power law, then so is this frequency, which is, it's going to be proportional to n of s, which is s to the minus alpha over n. Well, n is just a constant, so we can absorb that into this constant of proportionality. So if n of s is proportional to s to the minus alpha, then the frequency f of s is proportional to s to the minus alpha. So f of s is also a power law. So instead of plotting n of s on this chart, we could have plotted the frequencies against the size, and we would have also got a power law. The only difference being that the numbers on this scale would be different, but the appearance would be exactly the same. It would be another power law. Okay, I've drawn up here two possible distributions we could find in data. The first is our power law of s to the minus alpha, so it's just decaying, the number is shrinking with the size, and it's just going down and down. And the other is the normal distribution, which has a peak around a particular size, and then it decays on either side of that. And what we find is that with the normal distribution, firstly, there's a definite typical size, and secondly, that the values are clustered very close to that, and the chance of being much larger than it or much smaller is absolutely negligible. So it shrinks very quickly towards zero. It shrinks exponentially. In fact, it's even faster than exponential, because the formula is e to the minus a half s squared. So it shrinks even faster than e to the minus s. It's e to the minus s squared. So, you know, we find something like this, for example, in people's heights. So there's a typical average height of human beings. Let's say it's around 6 foot. Then we don't, you know, there's nobody who is 10 foot tall. It shrinks so rapidly that there's nobody even just a few, you know, less than double it. It's already impossibly small. And there's but with the power law, we can have people who are 6 foot tall, but there could be, you know, if human heights obeyed a power law, there would be plenty of people who were 10 foot tall, and on a planet the size of Earth with the population there would be possibly people who were 100 foot tall, and occasionally in history there would be people who were 1,000 foot tall. So the decay of the probability or the number with size for power law is much slower. So we say it has a fat tail. The tail is as you go to the extremes. And this is important because Mandelbrot, the discoverer of fractals, noticed this in the stock market. So what he noticed was that if we take a stock market chart and you take away the information on the axes, you can't tell what timescale that covers. This could be a day, it could be a month, it could be a year. Whatever this timescale, the stock market charts tend to look the same. The only way you would be able to tell the difference is if you had information about what these fluctuations are. So if this were a chart over a day, then these fluctuations might be, say, 10 pence. If it's over a month, then the fluctuations might be around about £1 up and down. If it's over a year, there might be £10 up and down. But if you take away that information about the scale, then it looks the same. In other words, it is scale free, scale invariant. In other words, these fluctuations have a power law distribution. And the problem was that people had assumed that the fluctuations in stock prices would have a normal distribution. They knew they were they treated them as kind of random, but they regarded them as random and normal. But as we've just seen, with the normal distribution, it means that they will remain within a fairly tight band. But in fact, they're power law distributed. So it means that very, very large fluctuations are still quite possible. And the models that people used for hedging against risk that assumed that they would remain within this narrow band were very vulnerable to the fact that actually the fluctuations could be much larger than their ways of handling risk had catered for. And if the exponent in the power law is less than 2, then there is no average value, no mean value. It's because if the alpha is less than 2, this decays so slowly that very, very large values are still reasonably possible, and so the average in effect becomes infinite, and so there isn't even a defined average, or you could say the average is infinite. Okay, so we've considered the possibility that we've got data that is distributed with the number of size s is a power law proportional to s to the minus alpha, and we know that that implies that the frequency of items of size s is also a power law proportional to s to the minus alpha. And so we might say that then that's the probability of an item having size s is a power law proportional to s to the minus alpha. We might wonder whether that's the case or hypothesize that. Just the same as if we throw a die 1,000 times, we'd find the frequency of 6s would be roughly 1 in 6, and we would say that the probability of a 6 is 1 in 6, exactly 1 in 6. So if the frequency is a power law, we might suggest that the frequency reflects the probability and the probability is a power law. But the trouble is that the data is never exact. The power law is only roughly visible, and there may be some deviations in the points from an exact power law. And it may be that it only looks like a power law within the limitations of the data. And so it may not be, in fact, exactly a power law distribution underneath it. And that's important because if we're developing models that assume it's a power law distribution, the true probability of the events occurring, when it actually isn't, then our models are going to be incorrect. They're going to be describing something that isn't real, isn't actually what we're seeing. And what we do find in many power laws in empirical data is that they look something like this. So let's put that's log of f, and that's log of s. So the red line is the data, and the power law is a straight line at high values of s, but at lower values of s, it kind of droops like this. So the power law would continue along the straight line, but the actual data is not on that straight line. So we say that the power law is in the tail. So the tail to the extreme large values of s. That's where we're seeing a power law. But in the lower values of s, it deviates from that. And so kind of sleight of hand that people might pull is to just focus on the tail and say, oh, well, look, there's a power law in the tail, so this is a power law. And kind of gloss over the deviation from that as though, well, that's due to some other circumstances, you know, well, what's going on in the lower values of s is something different. But what this is meaning is that the number of small items, or the fraction of small items, is less than we would expect. There aren't as many at the very small values as we would expect if this was a power law. And yes, it might be that there is a power law here that applies at these large values of s, and yes, there's something else here, but if we develop a theory for the power law, we're certainly explaining what's happening at this end. But let's consider what's known as a log normal distribution. Okay, so here is an ordinary normal distribution. The probability of size s plotted against the size s, and it has an average here is centered on 0, and you know it declines very quickly, as is the case with the normal distribution, so that we go 1, 2, 3. By this time it's become very small and negligible. So that's a normal distribution, but what we could do is say that let's consider these values here as not just the ordinary numbers, but let's think of these as logarithms of something. So 0, that would be the logarithm of 1, and I'll just use logarithms to the base 10 for simplicity. So 1 is the logarithm of 10, 2 is the logarithm of 10 squared, 100, 3 is the logarithm of 1,000. So if these are actually logarithms, then the underlying values are going 1, 10, 100, 1,000. So if this was an ordinary normal distribution, say for people's heights, so if we're calling the 0 is, let's say, 6 foot, then that's 6 foot, 7 foot, 8 foot, 9 foot, you know, and maybe there are some people who are approaching 9 foot, but beyond that it gets very small. But if these are logarithms, then it would be saying that, you know, there's say 6 foot, but then there can be 10 times out of 100, there could be people with 1,000 feet in height. If this were if these were logarithms, well, we know that that doesn't happen in heights, but it does happen in things that obey power laws. You get, you know, still very large values can occur with a reasonable probability. And if we take this log normal and plot it on a log-log chart, so we're now going to plot the logarithm of the probability against the logarithm of s. It looks like that. In other words, it looks exactly like, or very similar to, this kind of curve that is often found in empirical data. So the things that people might be identifying as power laws, and so, you know, when they're looking at the tail and calling it a power law, there might actually be, in fact, log normal distributions underlying them. Let's just write that up. This is a log normal. that's called. So we certainly need to consider that possibility that the data that we're calling a power law is actually a log normal distribution. Now, we will be talking about these distributions in more detail when we get to the statistics part of the course. But here I'm just pointing out this fact that when we're looking at power laws, there's always a possibility we might be confusing them with log normals. But we saw when we did the calculus part of the course that if we have a hyperbolic relationship, we can turn it into an exponential relationship by a transformation of variables, and vice versa. So an exponential can be made into a hyperbolic, and a hyperbolic can be made into an exponential just by transforming the variables in a certain way. So there's a sort of fundamental relationship between hyperbolic and exponential relationships. And the same is true between log normals and power laws, that it is possible to transform variables to make a power law into a log normal, or a log normal into a power law. If we see a log normal, it means that, yes, our data that we're looking at is not a power law, but there may be a power law in something less obvious. Okay, so we're now going to look at something called the cumulative distribution, or the cumulative probability, which is a useful way of looking at power law data. And we're going to be using ideas that we'll cover in more detail when we get on to the statistics part of this course. But we need these ideas now, so I'm having to introduce them up front. So firstly, I'll just define the cumulative probability, which we'll represent with a capital P, of sigma is equal to the probability that the size S is greater than or equal to sigma. So PR stands for the probability, and this says the probability that the size S of whatever we're talking about is greater than or equal to sigma, which is another size. So if we're talking about the cities obeying a power law distribution of sizes, we're saying, what's the probability the size of a city is greater than or equal to 1 million? Then that's the cumulative probability of 1 million. Or if it's wars, we're saying what's the probability that the severity of the war is greater than 1,000 fatalities? Then that is the cumulative probability of 1,000. So sigma is just a size, just like S is, but you now see why I've introduced the term sigma, just so we don't get confused. So it wouldn't really make sense to say the probability that the size S is greater than or equal to S. So it's just the size is greater than or equal to a given size, and that's the probability. So that's the cumulative probability P of that given size, sigma. Now, before we consider this in a bit more detail, we need to think a little bit about what we mean by this P, the probability of S that we were just talking about earlier. So if we've got the probability of size S plotted against S, we might have something like that. If we've got a power law, we know it's actually a curve down like this, but just in an arbitrary case. Well, this P of S isn't the probability of having a particular size S, because there are infinite number of points along here. There are infinite number of values of S. So the chance of landing on any one of them is 1 divided by infinity, which is 0. So P of S is has actual values. It's not 0. So what we're doing in plotting this P of S, we're talking about what is the probability density. It's how much is the probability of landing here. How does it compare with the probability of landing around here, or having a size around here? What's the how does the chances vary in this region compared to in this region? So it's the probability density, strictly speaking. Or is known as the probability density function, PDF. So we can't talk about the probability of at a particular point, because a point is just one among infinite number of points and has probabilities as 1 in infinity 0 landing on it. But we can talk about the probability of landing within a particular region here of a particular range of sizes. So that is the P of S times this range, which I'll write as little delta s, a range of sizes. But because we're dealing with we want to be exact, so we want to deal with very small regions, so we'll deal with infinitesimal regions. So we'll say this is a region from S to S plus ds, an infinitesimal. So it's of width ds, and so we can talk about the probability P of S ds. So P of S is actually a probability density function. Probabilities apply to ranges of values. Now it can be an infinitesimal range, but is nevertheless a range. So it is the P of S times D of S. So let's now think about this cumulative probability. This is sometimes called the cumulative distribution function, so CDF as opposed to PDF. Well, if we're talking about what's the probability of S being greater than or equal to sigma, so let's say we'll take sigma here. So we're adding up all the probabilities from sigma up. It's the size is greater than or equal to sigma, so it's from sigma up to infinity. We're interested in that probability, that what's above there. So we're adding up all the probabilities above sigma. So in other words, this P of sigma, capital P of sigma, is going to be the integral from sigma to infinity of P of S times ds. That's just summing all the probabilities, but doing it as a as an integral. Okay, so we can work out this if we know that we've got a power law. Then we've got P of S is proportional to S to the minus alpha, and we can make that exact by putting in a constant, which I'll just use capital C. So that's a power law. So how does the cumulative probability look for such a power law? Well, we've got P of sigma is then equal to the integral from sigma to infinity of Cs to the minus alpha ds, which is equal to, well, applying our laws for integrating powers, this will be, we add 1 to the power and we put that in front, so and divide by it in front, that is, so it will be C over minus alpha plus 1 times S to the minus alpha plus 1, and that's between sigma and infinity. And that is equal to, well, when we put in infinity, S to the minus alpha plus 1, This is negative, that's 1 over infinity, so it will be 0. So we've got 0, and then we've got minus c over minus alpha plus 1 times s, which is now sigma, to the minus alpha plus 1. And that, in turn, we could just simplify then. The 0 we can forget. And this minus sign here cancels with the minus sign on the bottom. So the bottom becomes c over alpha minus 1. And this is sigma to the minus alpha minus 1. We can write that as minus alpha plus 1 is minus alpha minus 1. And one thing we see from here is that alpha has to be larger than 1. If alpha was less than 1, then this wouldn't work. And what that means is that you can't have a power law distribution with an alpha less than 1, because it would mean that probabilities became infinite. You couldn't have a finite probability overall. So yes, alpha has to be less than 1. And we can now say from this then that, just putting it up again here, P of S is, sorry, P of sigma is proportional to sigma to the minus alpha minus 1. So in other words, the cumulative probability is also a power law. And we use sigma so as not to, so that we can write this and not to get confused between this size that's varying and the given size that we're measuring the cumulative probability at. So, but we could just write that as, now instead of sigma, we just write that as P of S is proportional to S to the minus alpha minus 1. So if the probability density is a power law, then the cumulative probability is also a power law. If the basic probability density has an exponent of alpha or minus alpha, then the cumulative probability has an exponent of alpha minus 1. Okay, we're now going to look at something called the rank size plot, which is a very useful tool for studying power laws. So let's start with a practical example. Okay, so here's an example taken from the work of George Zipf, who is a Harvard University linguist. He died in the early 50s, fairly young, I think. He was only in his 40s. And he did a lot of work on power laws in language and also in cities, the sizes of cities, the population sizes of cities. This is an example of the frequency of words in Alice in Wonderland. And we're plotting the size, which means the number of occurrences of that word in the book Alice in Wonderland, against its rank. Now, by the rank, we just mean that the commonest word, which is the, is rank 1, has rank 1. The second commonest word, which happens to be and, is rank 2. The third commonest word is a, which is rank 3. The fourth commonest word is 2, which is rank TO, 2, rank 4, and then she, which has rank 5, and so on. So in other words, it's if we put the words in order of how frequently they occur, that it's where they come in that list. from largest to smallest. So the is rank 1, and is rank 2, and so on. So we're plotting the size, which is how frequently they occur, against their rank. And we do it on a double logarithmic plot. And we typically find a straight line. And this is a sign of it being a power law. Now, as I've shown with this particular data, it deviates from the power law at the top here. So often we do see that. This is actually different from what I was talking about when I talked about log normals, because it also can deviate at the bottom, and that's where that's also fairly typical. Here these are in the extreme values in the tail, so in fact the tail is only itself a power law up to a certain point, and then it starts to deviate a bit. But in cities populations, for example, Zipf found really good power laws that all the way up to the larger values, and I think in some texts as well the power law is much better, and you get it looks like a power law all the way up to the top. So the point is that a rank size plot is related to the cumulative probability, and let's see how that works. Okay, so I've put up a table here showing the words the, and, to, she, and their size, the number of times that they appear in Alice in Wonderland. Well, I've just made up some numbers just for illustration. So let's say the appears 800 times, and 500, 300, to 200 times, and she 150 times. And then it will just keep going down, and there will be some words way down here that only appear once. And then we've got the rank here. So the is rank 1, and is rank 2, 3, 4, and 5. Well, I was just saying that the rank is equivalent to the cumulative probability. And that's because if we ask what's the cumulative probability, which is the probability that a word has a size greater than or equal to 800, which is the frequency for the. Well, there's only one word that's got 800 or more, because the is the commonest, so there's nothing above it. So there's just one word that is has that size or greater. So that is, in other words, if there were 2,000 words, distinct words in total, just to take a round number, then the probability of being 800 or greater is 1 out of 2,000. In fact, let's just be a little bit more general and call that n. And we'll just put 1 over n here. So, of all the words in Alice in Wonderland, there's only one that is of 800 or more. So in other words, 1 out of n words, 1 out of the n distinct words in Alice in Wonderland, 1 out of n, 1/nth of the words has a frequency of occurrence greater than 800. And then what are we, if we ask about what's the cumulative probability of for and? So that means what's the probability of a word being 500 or greater? Well, there are only 2 such words, because this is a rank 2. The only word above it is the, and everything else is less. So in other words, there are 2 out of n words that are equal to 500 or greater. And then similarly for there are just 3 words that have the frequency of a, which is 300 or greater. And for TO2 there are 4 out of the n words that have that frequency of occurrence 200 or greater. and so on. So we can see that these numbers here are just the rank divided by the total number of words. And that is the cumulative probability of S, the size, because that was our definition of the cumulative probability, the probability that the size is greater than S. So here it's the probability that the size is greater than 800, and we just been saying there, well, there's only one such, so it's only 1 out of n, so it's 1/n. And then here there are 2 greater, so it's 2n. So this is just the cumulative probability. So to repeat, rank is equivalent to cumulative probability just by a scaling factor of this constant value n. So let's now think about plotting various graphs. So we'll start with plotting the probability density, P of S against S, and I'll put, we're doing logarithms. Well, we'll assume we've got a power law, P is proportional to S to the minus alpha. So we know on the double logarithmic axes we'll get a straight line of slope minus alpha. And then if we plot the cumulative probability, that's capital P, going log, we've just seen that it is also a power law, so we'll also get a straight line, and though in this case the slope is alpha minus 1. And now what if we plot the rank, or rather the logarithm of the rank, for which I use the symbol R, I should have said. So log of rank against log of S. Well, we've just been saying that the rank is equivalent to the cumulative probability just by a scaling factor of n. So it will look exactly the same. It will just be shifted up and down by this scaling factor of n, which means it will be when we take the logarithm, there will just be log of we can say R equals n times P, the cumulative probability, so log of R is equal to log of n plus the log of P. So this is just a constant, so it will just shift up the graph, so we'll just start at a different point here, so then the numbers on the axis will be different, but the graph will look exactly the same, and it will have the same slope of alpha minus 1. Let's just get rid of that. Now, if we go back to what Zipf was doing, he was plotting not the log of the rank against the log of the size, but the log of the size against the log of the rank. So with the Zipf type rank size plot, we've got here log of R and here log of S. Well, if we have a straight line and we flip the axes, we still get a straight line. What changes though is the slope. So it just becomes 1 over the slope. So if we switch the axes, a 1 in 3 slope becomes a 3 in 1 slope. We just flip it over, take the reciprocal. So if we plot log of size against log of rank, we should still expect to see a straight line, but now the slope will be 1 over alpha minus 1. So we can say that if we've got a power law distribution in the probability, P is proportional to S to the minus alpha, then we'll also see a power law distribution in this rank size relationship. And specifically, we can say that the size S is proportional to R to the minus beta, where beta equals 1 over alpha minus 1. So if we do a rank size plot, we can measure the slope of it, which is the exponent beta, and then we know what the exponent of the underlying power law is, because the two are related by this. Now, Zipf did in fact favour this way of putting it, the log of the size against the log of the rank, though some people do plot it the other way around, the log of the rank against the log of the size. So, you know, one needs to be careful about that. A rank size plot sometimes may be the other way around, and so you need to check, because then the slope will be alpha minus 1, not 1 over alpha minus 1. But I find this more intuitive, so I think the rank size plots that we will use in this course will be of that kind, the Zipfian style. Okay, let's just say a few more words about that. So what we're saying is that if we have a power law distribution, so the probability of size S, the probability density function is proportional to S to the minus alpha, then we have a relationship between the size of an item and its rank that is also a power law. S is proportional to R to the minus beta, where beta is 1 over alpha minus 1. And so Zipf studied particularly these kinds of relationships. He looked at how the size depended on the rank. And this is sometimes known as Zipf's law, that we find power laws in things like the populations of cities, or the frequencies of words in written text. And Zipf went a bit further, because he strictly, Zipf's law is that beta is 1. This is what he found particularly remarkable. It's not just any old power law, but it's a power law with a beta, an exponent of 1. So if we looked at our Alice in Wonderland data there, the value here, the slope of the rank size plot, so that's log S against log R, is minus 1.025, so it's very close to minus 1. And Zipf found this also in cities and in many other written texts. It always seems to come out to 1. So that is kind of Zipf's law in the strictest sense, that it's not just S is proportional to R to the minus beta, but S is proportional to R to the minus 1. And we can put a little subscript there, so SR. So the size of the item ranked R is proportional to R to the minus 1. And so we could say that SR equals some constant K times R to the minus 1. But what about when when the rank is 1? Then we'll have S1, the size of the item ranked 1, is going to be K times 1 to the minus 1. Well, 1 to the power of anything is 1. So S1 equals K, or in other words, K equals S1. So our sort of Zipfian rule is SR equals S1 times R to the minus 1, R being the rank. Which we could also write as S1 divided by R, because R to the minus 1 means 1 over R. Well, this means then that a very simple rule, that the item of size 1 is just S1. The item of rank 1 has a size S1. The item of rank 2 has S1 over 2. So in other words, it's just half the size of the largest. The item of rank 3 will be S1 over 3. So it will have size S1 over 3. It's just a third of the size. And the fourth one will be divided by 4. So it will be a quarter of the size of the largest. So the values will be S1, S1 over 2, S1 over 3. Well, if these are the ranks, R, that's versus size, 2, 3, 4. S1 over 4, and so on. So it's a very simple relationship. So for example, Zipf found that there was this kind of rank size relationship in the populations of American cities in his day. So let's say the largest was New York and Los Angeles was the second largest. Then that meant that Los Angeles was half the size of New York. That's what he found. And then that if it's Chicago, say, was the third, then Chicago was a third the size of New York, and so on. And the city that came 10th in size was a 10th the size of New York, etc. So that is a Zipf law in the strictest sense. But Zipf was also interested in the way that these coefficients here, or exponents, sometimes deviated from the exact value of 1, and we'll consider that in a moment, his ideas about that. But so if we had such a generalized relationship that SR equals S1, if F was proportional to R to the minus beta, then that would mean that SR is, we could write it as S1 over R to the beta, because we will still find that the constant is S1, because when rank is 1, that's 1 to the beta. Well, 1 to the power of anything is 1, so S1 equals S1, which is correct. So in general, if the rank size has an exponent of beta, then the sizes of rank R will depend on the size of rank 1 by this kind of relationship. There'll be an R to the beta on the bottom line instead of just R. And one last thing to mention is that we're calling this a rank size plot, but some people call it a rank frequency plot, because we saw that with the words in Alice in Wonderland, the size was the frequency with which the word occurred in the text. So, you know, I use the example that the was 800 because there are 800 times that the appears in the text. So the frequency is of the is 800. That's how frequently it appears. So sometimes it's called a rank frequency plot, but it's the same thing. Okay, we're now going to talk about the ideas of unification and diversification, which is something that Zipf came up with. But you know, his concept has kind of fallen by the wayside. I don't really see people using it today. And that's probably because his explanation of it was rather confused. And he sort of tried to prove what he meant with some mathematics, but his mathematics doesn't really work. Yes, I think people have kind of neglected it, but I think that's unfortunate, because I think the ideas are really quite useful as a way of thinking about power laws, and they can be made more rigorous. So let's just talk through his idea here. So he, to take the example of language, we get power laws in language. He suggested that this was the result of a tension between what he called forces of unification and diversification. And the reason you get a power law with a slope of 1 is because that represents a kind of balance between these two forces. So again, taking the example of language, he said that when a speaker communicates with a listener, from the speaker's perspective, it's desirable to pack a lot of meaning into the words that you use. So you you know, it takes a lot of effort to try and find exactly the right word to convey the meaning that you're thinking of. So it's helpful if you've just got a word that covers a wide range of meanings and you can just use that word. So the person speaking wants to concentrate meanings into just a few words. So they just have a few words to select from and not try to, you know, find the right word amidst thousands of possible words. But from the listener, it's the other way round. They want many different words so that they can quickly grasp what the speaker is saying, so that they want the speaker to be precise, not force the listener to try and work out from the context what particular meaning the speaker is trying to communicate with that word. So Zipf said that the reason then we have a situation where we've got some words that are very common and have a wide range of meaning, and other words that are much more specialized but fairly rare, is because of a tension between these two forces. It's a kind of balance that occurs. It's a compromise between the speaker's desire to concentrate all the meanings in a few words and the listener's desire to spread the meanings out into many different words to get, you know, so that each one conveys a very specific meaning. So if, for example, we take the commonest word in English, the, you know, that has a very wide range of meanings. It sort of basically means something like that thing, you know. The. If we, but for the listener, you know, if you just say the what, you know, so you then use a more specific word, the car, and now the listener is on board with you. So the is very common, car is a less common word, but then you could become more specific. You know, you could say the Lamborghini, what particular type of car, and then you're being very specific, but the word Lamborghini is much rarer than the word car, which in turn is much rarer than the. So the covers an awful, you know, very large range of situations. Car covers a smaller but still relatively large range of situations. Lamborghini will occur only rarely in very rare situations. So what Zipf is saying is that the speaker just wants to talk about the car. For them, it's not important to go precisely which car. It doesn't really matter. You know, don't make me try and remember exactly what car it was. It's just a car. Whereas the listener is saying, you know, no, you know, so I can picture this scene clearly. You know, I want to know precisely what kind of car it was. You know, so the listener wants to know that it's a Lamborghini so that they can really understand what's going on. But the speaker just doesn't really want to bother to rack their brains to, you know, to remember that word Lamborghini to specify exactly what it was. So it's this contest between the listener's desire for specificity and the speaker's desire for genericness that creates this balance, so that we've got some very common words with pack a lot of meaning, but also for, you know, necessary situations we've got more detailed but rarer words. So if we then look at the rank size plot, we've got a straight line of slope -1, which I've just put as 1, just assume the minus sign in front of it. So Zipf suggested that the reason it is 1 is the result of this balance between the forces of unification and diversification. The speaker trying to unify meanings into a few words, the listener wanting to diversify them into many specific words. And then Zipf said, what happens if the slope is less than 1? Greater than 1. Let's do first. So it's a steeper slope. That's supposed to be a straight line. A steeper slope. So here, I'll put that's beta, the slope. Beta equals 1. if beta is greater than 1. He said this occurs when the forces of unification are stronger than the forces of diversification, because a chart like this, if that's the way that the size depends on the rank, it means that the sizes fall away very quickly as you go to higher ranks. So it means that the commonest one is very common. If it's the word that will occur overwhelmingly often compared to other words. Even the second one down is already fallen behind quite a way. So a steep slope like this means that the force of unification is winning. U is greater than D if we use the letters U and D for unification and diversification. And then what if we went to the absolute extreme of a vertical line like this? Well, here the slope of a vertical line like that is infinite. You go up, you shoot right up in the space of 0. So the slope is so steep it's infinite. And in this case, Zipf would say the force of diversification is 0. Or equivalently, the force of unification is infinite. Because what this means is that the first ranked item has some value, and then the others are way down on the logarithm at minus infinity, which means 0. So all other words never occur. They have a probability of 0 or a size of 0. So this is maximum unification. You've got just one word which would carry all the meaning, and no other word ever appears. And then if we go the other way, if we have a shallower slope, so let's just give myself space, so that's beta equals 1. So here we've got now a slope of less than 1. And here Zipf would say that this occurs when the force of unification is losing compared to diversification. So the force of unification U is less than the force of diversification, because what this means is that the frequencies or sizes of the other items, the frequencies of the words in the text, fall away more slowly. So even at quite high ranks, the less common words, they're still occurring pretty often compared to the highest ranked one. So the meanings are tending to be diversified into many words. And then if we take the extreme where we've just got a horizontal line, so the slope is 0, it's neither going up nor down, it has no slope, it's 0 slope, then in this case Zipf would say the force of unification equals 0, because in this case all words of whatever rank occur with the same frequency. They all occur equally often. So there is absolutely no unification into particular words. No word is more common than any other. So there is 0 unification, and conversely there is maximum or infinite diversification. The meaning is spread out into potentially infinite number of words. And we could then sort of relate these in this diagram by suggesting that the slope, the exponent of the power law, is equal to U over D. Because then that would explain this. If the forces of unification and diversification are in balance, so here, this was Zipf's original sort of hypothesis, that the slope is 1 because unification equals diversification. They're equal. That's kind of the ideal compromise when the two forces balance. And of course, if U equals D, then it would be U divided by U. This will be 1. If U is less than D, then if u is less than d, then beta is less than 1, which is what we found here. If the force of unification is 0, then beta equals 0, which is what we've got there. And then over here, if u is greater than d, then beta will be greater than 1. And if either diversification is 0 or unification is infinite, we've got beta equals infinite divided by 0, infinite. So we can explain this then in his terms, that the slope of the power law reflects the balance between the forces of unification and diversification. Specifically, beta equals u over d. So when we've got a power law like, or in a rank size plot, SR is proportional to R to the minus beta. That's really R to the minus u over d, where u and d are these forces of unification and diversification. The problem is this is all kind of hand waving and qualitative, because Zipf didn't really suggest any way that we can measure the forces of unification and diversification, so that we could actually test this. It's more conceptual. But we're going to come on to in a little bit later in this lesson to see how we can perhaps find a more of a mathematical logic behind it. Okay, we've just been talking about rank size plots. And we've seen that the slope of this line is kind of a measure of the inequality, the unequalness in the data, so that some items with the highest ranked ones, now I should perhaps pause here to say there's kind of a bit of a confusion, isn't there? If I say the highest ranked, 1, 2, 3, we're talking about the high ranks, so the first, second, third, but the lowest ranked would be, rank 100, rank 1,000, but 1 and 2, 3 and 3 are lower numbers than 100 and 1,000. So when we say the lowest ranked, do we mean the lowest ranked because they're the low numbers, 1, 2, 3, or do we mean the ones that are ranking down here, coming far down in the order, rank 100, rank 1,000, which are the high numbers? Some people might use the terminology the different way around. By lowest rank, they might mean these ones, ranks 1, 2 and 3, whereas I'm tending to use lowest ranked to mean actually the high value numbers. So let's just be clear about that. There is a bit of a confusion. So the highest ranked for me are the top ranks 1, 2, 3, 4. And the lowest ranked are the bottom ranks, 100, 1,000 and 1,000,000 and so on. So so when we look at a rank size plot like this, it means that the highest ranked items, 1, 2, 3 ranks, they're very large, and then the lower ranked items are very small. So if this is a plot of people's incomes, for example, it means that the highest ranked people, the top people in the country, have very large incomes, and the lowest ranked people have very low incomes. So this is showing us something about inequality. And then what we've seen with this unification and diversification idea is that the steeper the slope, the greater the amount of unification. So a steeper slope means more inequality. The highest ranked items have even more compared to the lowest ranked ones. And if we go the other way, this is less unequal. The lowest ranked items still have a reasonable size compared to the highest ranked ones. So on a rank size plot, the steepness of the slope is a measure of the inequality in the data. That's it's a measure of this balance between unification, trying to create more inequality, and diversification, trying to create less inequality. So this is a good place to introduce something called the Gini index, which is another way of measuring inequality in data. So let's have a look at that. Okay, so we'll use the example of wealth in a population. So on the x-axis here, we'll plot the fraction of the population, which can go from 0 to 1. And in the vertical direction, we'll plot the fraction of the wealth possessed by that fraction of the population, and which can again go from 0 to 1 or 100%. Well, if everybody had equal wealth and we plotted this so-called Lorentz curve, it would just be a straight line. That's supposed to be a straight line. Because that would mean that, you know, if we took the first 10% of the population, they would have 10% of the wealth. And then the next 10%, so up to 20% of the population, that would be 20% of the wealth. So it would just be a straight line, in fact, of slope 1 going from 0 to 1 diagonally across this, and it would just go up smoothly. If we add 10% to the population, we add 10% to the amount of wealth that they have. But as we know, that's not the case in real economies or societies. If we plot the fraction of the wealth against the fraction of the population, we get a curve that looks like that. This is then the Lorentz curve. So what this means is that if we take the first 10% of the population, the lowest income or lowest wealth part of the population, anyway, the lowest 10%, then they have less than 10% of the wealth. You know, they might only have 1% of the wealth. And then we go up to the 20%, it's still very low. It's, you know, maybe only 5% of the wealth. And the 30% of the population only has sort of 8% of the wealth. And then, but then when we get to here, when we go for the last 10% of the population, they have, you know, 30% of the wealth. So we jump from the last 10% from here, 70%, all the way up to 100%. So the last 10% has 30% of the wealth. So this is a measure of the inequality. The lowest percentage, the lowest segments of the population have a less of a fraction of wealth than they are as a fraction of the population, and the highest and most wealthy parts of the population have a larger fraction of the wealth than they are as a fraction of the population. So, and the more bowed this is, the more that is the case. So that, you know, in the extreme, if nobody had any wealth except the wealthiest person, this would just go right along the lines of the box. Everybody would be 0 till we got to here, and then the last person would add 100% of the wealth. So the further away this is from the straight line, the greater the inequality. And the definition of the Gini index is that we take, if we call this area here A, and the area below this curve B, so A is the area of this slice of orange type shape here, then this measure of inequality is defined as A over A plus B. So it's the area of that segment over the whole corner of this box here. So that we said that if there were complete equality, it would go along this line. So A would be 0. And so this inequality would be 0. Whereas if one person had all the wealth and everybody else had nothing, it would go along the sides of the box here. So A would take up the whole of A plus B. So that would be A over A. B would be 0. So that would just be 1. So the inequality index varies between 0 and 1, and a value of 1 means high or indeed maximum inequality, and in this direction the lower values mean lower inequality. So that is the Gini index. As I said, it's another way of measuring inequality, not just in wealth, but in any kind of data. You know, we could do, there might be the population sizes of cities. So it's we plot the cities along the bottom, the fraction of the cities, and what part of the population of the country they have. So the 10% smallest cities would have a fairly small share of the overall population, and the largest cities would have a disproportionately large share of the total population of the country. So we can measure inequality in any kind of data using this.